Hi, my name's Tom Falconberry, and I'm at Tarleton State University. And today my MathPsych talk is on a hierarchical Bayesian shifted Wald model with censoring. Now, it's likely very well known to this group that response times are indeed a classic measure of cognitive processing. In fact, in the preface to his classic book on response times, Luce indicates that we surely do not understand a choice process very thoroughly until we can account for the time required for it to be carried out. So certainly in the field of cognition and any of the subfields within, my own field is numerical cognition, RTs are what we deal with every day. They are indeed the thing that informs our understanding of the latent processes, those processes that we cannot see, that are involved in the various decision-making tasks that result in the behavior that we analyze. Now, most of you probably know the classical technique for dealing with response times in these kinds of experiments is to first have people do a bunch of trials. Right? And then maybe it's a bunch of button presses or mouse clicks on a screen, and we measure the response time, usually in milliseconds, of each one of these trials. Okay, now what do we do with all of that? Well, usually we find the mean response time for each experimental condition and person. So we look at all the design cells, we've got this many people with this many conditions if it's repeated measures, and then we find the mean in each one of those conditions. And then what we do is we submit all of those means, or sometimes medians, but those single numbers in each condition into some sort of statistical test where we can test for differences in means, usually with an ANOVA. Now this method is very lossy, right? It collapses each person's response time distribution to a single number, the mean or the median. That's a lot of information that's being lost. So is that a bad thing? Well, I would argue that it is. So for one thing, the mean, if we just focus on that, the mean does not uniquely identify the distribution of response times that it came from. So as you can see in the figure here, we have 4 different distributions. Each of these distributions has a mean response time of 3/4 of a second or 750 milliseconds. Yet these 3 distributions are all very different, and as such they would indicate a different behavioral signature. There's likely different things going on cognitively speaking that would lead to a distribution of those specific shapes. So what we want to do is get a little more information from our response times, not just the center, but more about the shape itself. So we need a way to capture the distribution of response times. Now, one of the gold standards to use for capturing the distribution of response times is the diffusion model. Many of you are probably very aware of the diffusion model. Now, one problem with the diffusion model is that estimating diffusion parameters does require you to have some error trials. In fact, it requires a sufficient number of valid error trials so that you can uniquely identify the parameters. But in some tasks, particularly the kinds of tasks that I often use in my own work with numerical perception and numerical processing, some of those tasks, errors are quite rare. People are really good at these tasks. And so you have to think about experimentally, well, how do I make people make more errors? Is there a way that I can estimate diffusion model parameters in tasks where the error rates are low without having to make the tasks artificially hard? And the answer is, well, yeah, maybe. So one approach that we might take is the shifted Wald model. Now this approach works because it's a single, or it's just like the diffusion model in that it is an accumulator that accumulates noisy information as it drifts towards some response boundary. Okay, so this is a typical diagram to illustrate where the shifted Wald distribution comes from. So you have some sort of non-decision time here. This is not related to the accumulator. And then once the accumulator starts, there's a stochastic process that's going on here. It's a noisy accumulation of information. It drifts toward the boundary, so the average rate of information uptake is some number. It's like 2 in this case. And then it finally drifts toward until it stops, it hits a boundary, and that's the response time that's elapsed. So in this case, this is looking at about 750 milliseconds. Now, the one issue here is that this is a single boundary accumulator. So errors are ignored. The diffusion model has 2 boundaries, and so you can nicely model correct responses and errors by considering those as opposite boundaries from each other. But this is a single boundary accumulator. So in my own work, when I've used the shifted Wald model before, the way you get around that is you just throw out the errors. I mean, it works, but I would like to keep those errors. I would like to involve those in the modeling process somehow. Another issue with the shifted Wald model is that the parameters you get when you estimate shifted Wald parameters do not uniquely correspond to the diffusion model parameters. So this is something that was first pointed out by MathPsych and Wagenmakers in 2009. So that's really a big problem as well. So can we improve on this? So our goal is to somehow fix or augment the shifted Wald model so that it can account for the albeit small number of error trials that we usually see. And one solution that I want to pursue today is to use what's called a censored shifted Wald model. Now this was an idea first proposed by Miller et al. In 2018, and it basically works as follows. So here we have a diagram very similar to the one on the previous slide where you've got some non-decision time and then you've got an accumulator that starts. So that's the black line that you see here. And so the RTs on correct trials might look something like this. You've got this noisy accumulation of information until you hit the response boundary. But now how do you deal with errors? Okay, so there's not another boundary down there. But what if we were to consider a diffusion model-like boundary? So this is not a real boundary, but like an artificial point, so that when you get an error trial, you can consider the response time of that error trial as simply an artificially censored accumulator. Okay, so the idea here is that on that trial, the gray line that you see, when it's accumulating information, if you hit an error, that accumulator ideally would still be considered to accumulate toward the correct boundary eventually if you let it, right? So if you press a button and you get it wrong, what you've really done is you've censored or stopped an accumulator before it had time to fully realize itself toward the correct boundary. And so censoring in this context is exactly how the censored shifted Wald model handles errors. It considers error trials as trials which have been censored, and the censoring time is itself a random variable. Okay? So that's kind of a conceptual description of what a censored shifted Wald model looks like. How do you actually do that? This, for my own work, I thought for a long time, how do you actually make this work? And it turns out it's really pretty simple. So here's how you build a likelihood, right? If you want to do any sort of parameter estimation, you need a likelihood function. So here's how you do it. So first of all, if a trial is correct, then it's no problem. This is basically your shifted Wald model. So what you know then is that the likelihood follows directly from the density function itself for the shifted Wald. So in this case, the likelihood of these three parameters given some observed response time is just the density function of the shifted Wald. And that's this guy right here. So then you can use your favorite parameter estimation technique to essentially get like if you use maximum likelihood estimation, you would maximize the likelihood function of the parameters gamma, alpha, and theta against that observed x. So that's no problem, right? But what about when you have error trials? So if the trial is incorrect, then the censored shifted Wald considers that the accumulator toward the correct boundary is still going, and that the recorded response time is just something that's been randomly censored at some point prior. So in this case, the likelihood doesn't come from the density function, but rather it comes from the survival function. So the survival function is the probability that the process is still going, right? And one way to think about that is it's the probability that it hasn't stopped yet. So it's 1 minus the cumulative distribution function. And so if you know the cumulative distribution function for your model, in this case the shifted Wald, then getting the likelihood function is just the survivor function, 1 minus, and then all this stuff that you see here is just the cumulative distribution function. Okay? So conceptually, that's pretty simple. So how do we put this all together? You've either got one thing or another. You've got a correct trial or an incorrect trial. So let's consider a collection of n observed response times. If you want the likelihood, well, they're all independent trials. We put that assumption on there. Then the likelihood is just going to be the product of all of those likelihoods. So what we do here is, for computational convenience, we just simply say it's the product of all the trials plugged into the density function and the product of all the trials plugged into the survivor function. And then what we want to do is basically turn on the density function when they're correct and turn it off when they're not. and simultaneously turn on the survivor function when it's incorrect and turn it off when not. And the way we do that is we just raise them to this power, 1 minus di or di, where di is a censoring indicator. Di is equal to 0 if it's a correct trial and 1 if it's an incorrect trial. So what does that get you? Well, if it's a correct trial, then the exponent on all these is 1. So for the correct trials, you're using the density function and you're not using the survivor function, and vice versa on the incorrect trials. If the indicator is 1, then this 1 minus 1 becomes 0, and so that all goes away and you're just using the survivor function. So that's it. That's all that you need to do. And then, of course, whatever kind of estimation method you want to use, you just want to find the log likelihood. And of course, we use our typical log rules to turn products into sums and then bring the exponents down and all of that good stuff. So that's actually a little bit of a typo there, and I'm sorry for that. That should be 1 minus di times the log of the density function. Okay, but that's not important for this. What is important for this talk is that I want to describe a hierarchical Bayesian extension of this idea. So Miller et al. Did all of the stuff that I just talked about, where they used maximum likelihood estimation to show that the censored shifted Wald was actually able to recover diffusion model parameters quite nicely. So what about a hierarchical Bayesian approach? So here we would consider all of our data as being a bunch of trials nested within subjects. Subjects would then have subject-specific values for response threshold, for non-decision time, and for drift rate, and that those would then come from some parent level distributions. Okay, so what I did was take that idea from MathPsych and Wagenmakers, and then I combined the kind of classic parameter recovery technique of Farrell and Ludwig to do a parameter recovery experiment. So here we assume that individuals have distributions of response times that have drift rate, response threshold, and non-decision time parameters unique to each person, but those are all in turn drawn from population values that we will fix in just a second. So the design was as follows. We have 1,000 simulated data sets in each of the following 3 factors. So I looked at maximum likelihood versus hierarchical Bayesian. I looked at censored versus non-censored. And I looked at error rates being low versus high. Now these are just total made up labels, but I wanted to see whether smaller error rates versus bigger error rates made a difference on our estimation. And then within each of these conditions, we varied both the number of participants and the number of trials. We used the 5 combinations that Farrell and Ludwig did. These are kind of classic at this point, and I'll present them now. What are the targets? Well, I made up some targets. The target drift rate for all of these simulations was 0.8. Boundary separation depended on the error percentage, so a little smaller if it's higher errors, a little bigger if it's smaller, and then a fixed non-decision time. And we assume that the start point of the accumulator was in the middle. Okay. So let's look at some of these. There's a lot of figures here, and I'll give you a link in a second that you can go to see all of these slides in detail. But let's just look at drift rates first. So first of all, the thing that you might notice is that the censored versions, whether it was maximum likelihood or Bayesian, tended to produce better estimates. So the gray line is the target value. And so with a small number of participants, small number of trials, we increase the number of trials. Notice, even especially in the high error case, the censored version is getting closer to the actual target than the non-censored. Notice they're getting certainly crisper to where you can't really tell the difference between Bayes and MLE anymore. Now, when we go to a higher number of participants but small trials, again, Bayesian inference gives you much better precision on your estimates and certainly more accurate in this case. And even so, censored gives you more accuracy than non-censored. Let's move on to boundary separation. Boundary separation is terrible to recover for maximum likelihood estimation, but Bayes handles it no problem whatsoever. Now, of course, that gets better as the number of trials increases to where it's getting harder and harder to tell the differences. Again, when we get to small number of trials per person, MLEs all over the place, whereas Bayes is pretty crisp. Okay. And then non-decision time, kind of the same thing with small number of trials. The recovery is terrible for MLE, but Bayes does better, and censored does just even a little bit better than that. Okay. So A lot of stuff there, but we got some interim conclusions to begin working with here. So first of all, censoring does seem to improve the shifted wall parameter recovery, especially for drift rates, and even more so when the error rate is a little higher. And important to this talk, using hierarchical Bayesian version of the censored shifted wall model makes parameter estimates more precise compared to MLE, especially with small sample sizes. So big sample sizes, use what you want, but if you've got small sample sizes, hierarchical Bayes is your friend. And I will just mention in passing that the model is relatively easy to implement in Stan, and I've got a link here. It's at my GitHub page, so github.com/TomFalkenberry/censored shifted Wald. If you go there, you'll see, let me just open it up real quick so you can see what it is. On my GitHub site, I've got a script that I use. I've also got the Stan model itself, so you can get in there and play around with the code. And of course, if you have any questions about all of that, it's kind of use at your own risk, but email me and I'm happy to visit with you about that. So that's all I wanted to say about the censored shifted Wald. So thank you for listening.